Okay, well, I'd like to thank the organizers for inviting me here to speak. It's a great honor. Yeah, so that's the title of my talk. And well, so I'll try to make the title precise, my talk, but it's about really representations of p-adic field, smooth representations of reductive groups over p-adic field. So let F be a p-adic field, and G a connected reductive group over F, and maybe I'll put a wide hat. So let GF hat to be not the Langlands dual group, but a set of irreducible unitary representations of GF up to isomorphism. So, usually it's referred to as the unitary dual of GF. And well, I'm not truly a representation theorist, but assume that for a moment. And if I were a representation theorist, then one of the ultimate goals would be to understand the unitary dual. By that, by understanding, I mean, maybe you want to classify all unitary representations and give some good description of this. Oh, by the way, I wanted to begin by apologizing because you see the title of the conference is on the Langlands program, endoscopy and beyond, or beyond endoscopy, but somehow my talk is not so relevant, unfortunately. It's not about the Langlands program and has little to do with endoscopy or beyond endoscopy, but it's before endoscopy. Yeah. Right. So I'm kind of doing a baby local version of what people might be interested in beyond endoscopy, but still it's much softer. And yeah, so actually there's no automorphic representation, no Langlands parameters or orthoparameters, no algebraic geometry. Yeah, so yeah, it's quite, yes, maybe, yeah. That's a best interpretation of what I intend to do. Well, and yeah, so don't be too disappointed if things stay elementary. Okay, so we want to understand the unitary dual, but well, actually, of course, my goal is much more modest, and I want to concentrate on the following vague question about the structure of unitary dual. So what are kind of most non-tempered representations, non-tempered unitary representations, so say representations in this guy. So it's just a rephrase of my title, and well, before I interpret this more precisely, let me just mention a couple of motivations. So first of all, well, identifying unitary dual is important because if you're interested in global arithmetic, then, well, local components of an automorphic representation are unitary, so that gives you some constraint on what local components of automorphic representations can be. For instance, this could be a first step toward things like Ramanujan conjecture. Very first step. Of course, the bound you're going to get won't be very good, but still, you get some non-trivial information. And another thing is, this is a little bit vague, but we've seen some sort of asymptotics on the geometric side of the trace formula, and then the general philosophy there is that, well, the dominant term comes from central elements in the geometric side of the trace formula. If you look at the spectral side, then in some sense, the spectral side, the asymptotics in the spectral side is going to be governed by or dominated by these most non-tempered representations. So it's kind of identifying leading term in the spectral asymptotics, whatever that means. I mean, in my intended application, I have a specific meaning, but let's just keep it vague. And now let me get to what I mean by this. So for I mean, there's no universal agreement. So I'll just list some possibilities. So one interpretation is, well, if you somehow have A packets or A parameters, then well, I mean, it was mentioned also in Nicholas's talk this morning, but basically the SL2 part of the A parameter is going to tell you how non-tempered it's going to be. For instance, the most non-tempered thing would be the A parameter such that the image of SL2 contains the regular unipotent elements in the Langlands dual group. But that's not really what I want to do, and one reason is that A packets are not going to exhaust unitary dual. For instance, you're going to miss out complementary series. So, but I'll just mention that there's also, I mean, it's still kind of in the spirit of Nicholas's talk in some sense, but if somehow your representations, unitary representations contribute to the cohomology of certain, well, algebraic geometric objects, such as cohomology of locally symmetric spaces or Shimura varieties, then, well, usually the tendency is non-tempered representations. Tempered representations tend to contribute to the middle degree, and as you go to extreme degrees, top or bottom degrees, you get more and more non-tempered. So in this regard, most non-tempered would mean that your representation is appearing in top or bottom degree of cohomology. And also in that case, if you're in a situation like as in Nicholas's talk, then maybe the asymptotics is going to be governed by the highest power of P, and then that's going to be governed by the kind of extreme degrees of cohomology. And these two are actually related. It was also mentioned that SL2 here somehow has to do with Lefschetz operator in cohomology, but that's not what I'm going to talk about, not quite. There's some more easier and intrinsic ways to think about this. For instance, well, we all know about parabolic induction, perhaps, and then you can just look at the inducing data. Well, by that I mean, well, your unitary representation is going to appear in some parabolically induced representation. Now you have some Levy subgroup and a representation on that. Well, and you measure how non-unitary it is on the Levy subgroup. So for instance, you can look at the central character of the representation on the Levy subgroup and then see how it deviates from being unitary. So, and similarly, you can look at the Jacquet module. Well, take the Jacquet module and look at the central characters and now measure how non-unitary they are. So and I mean, obviously they are related. I mean, they are not totally equivalent, but they are closely related. And another related thing would be if you look at the location of pole of local L factor when it's defined, then I mean, these three are closely related. And they're not really equivalent to each other, but I mean, these are possible interpretations. And now I'll just say that this is the one I'm going to look at. Well, this talk is about the Jacquet module interpretation of non-temperedness. So as I said, it's about the central characters of Jacquet modules along proper parabolic subgroups. So I'm going to make this precise, but before that, well, for people who haven't thought much about unitary representations, I'll just give a quick example. When you have, or GL2 or maybe PGL2, just keep the central character trivial. And you look at the unitary, or unreified part of the unitary dual. So, and then, well, you can. And then, I mean, here's kind of rough picture of what's going on. There is a big tempered locus. In fact, in some sense, most representations are going to be tempered, but, well, here's a explicit parameterization. So it's going to be, well, there's a family of unreified tempered representations parameterized by those induced from absolute value character to the IT, the absolute value character to the negative IT, where T is real. And I mean, maybe there's a suitable identification, like modulo 2z, 2 pi z or something. Maybe, well, I'm not, maybe not quite, maybe I need log, or whatever, modulo something, some lattice. Okay, and then there's also another family of representations, complementary series representations induced from the representation on GL1 times GL1 given by absolute value to the A and to the negative A, where A is a real number between 0 and 1/2. So here's like A is 0. Here's like A is 1/2, but you consider things strictly in between. And then there's this trivial representation, which can be thought of as Langland's quotient of the representation induced from absolute value to the half and negative half. So here, every parabolic induction is normalized. And the point of my talk is really to identify this guy that's kind of the farthest away from the tempered locus. So it's this guy, which is the trivial representation in this case. Right. So I'm going to mention that here, of course, I'm looking at unreified part. So I don't see it, but Steinberg is a discrete series representation and it's kind of isolated. And actually, that's a great question because, or comment, because we'll see how to distinguish between trivial and Steinberg. Of course, if you just look at the inducing data, then I mean, they appear in the same principal series, so you don't distinguish. But when you look at the Jacquet module, we'll see the difference. And basically, I like to identify this guy in some quantitative way. Okay, are there other questions or comments? Right, yeah, I mean, the second most tempered, non-tempered. Well, here, you cannot quite do that because of, well, you can get arbitrarily close to the trivial representation. And in certain situations, the trivial representation is, or one-dimensional representations are isolated. And, well, maybe I'll comment on that. But yeah, there's Cauchy property T, and there's a kind of bound on that. But yeah, it's a kind of separate issue. Okay, are there anything else before I move on? Yeah, well, there is a close relation to asymptotics of matrix coefficients. And yeah, we'll actually see it later in my talk. Okay, so let me now make this version precise. So that's going to be the conjecture. So I'll erase this now. Okay, so the conjecture. So to formulate this, I'll introduce some notation. So P is, and I'll write often G for G of F. Maybe that's a standard abuse of notation. And also unitary would also mean unitarizable smooth representations. Okay, so it's a proper parabolic, and there's a Levy decomposition. M is Levy, N is unipotent radical. And delta P, the modulus character, I'll just recall the definition, which is going to be important. So if I have an element of the Levy, then by adjoint action, M acts on the unipotent radical. So I look at the determinant of this action on Lie algebra of N and take the p-adic absolute value. Okay, I think I need to introduce maybe also AM, which is the maximal split central torus in M. Maximal split torus. And also there's this Jacquet module. Again, for the sake of completeness, I'll just recall the definition, which is whenever you're given representation of G, say smooth of finite length, you get a representation of M. The way you get it is you restrict G action to the P action and then take the N invariant. Then you end up with an M representation, and to normalize, you twist by delta P negative 1/2, which is a character of M, so everything makes sense, and actually it's a functor, and that's my dear Jacquet module. Okay, so finally I'll define exponents, which are just another name for central characters appearing in the Jacquet module. So just central characters in JP of pi. I don't care about multiplicity. I just look at all possible central characters. Obviously, it's a finite set because Jacquet module sends finite length representations to finite length representations. And here's the precise form of the conjecture. So let pi be a unitary representation. And, well, I like to pick any exponent. And I take a co-character. In fact, I'll consider just algebraic co-character, or actually rational version of that is fine. But let's say this is P positive in the sense that when it acts on the algebra by the adjoint action, then nu and adjoint, then the weights are all positive. So I hope that makes sense. I mean, there are other ways to phrase this, but, well, GM acts on a vector space algebraically, so, well, the weights are integers, and I'm just requiring weights to be positive. So in the p-adic topology, it's going to be contracting, basically. Okay, then there are two parts. First of all, the absolute value of the central character at nu of p is going to be bounded by delta p negative 1/2 of up. And moreover, equality holds if and only if pi is finite dimensional. Okay. And, well, to relate to the title of my talk, somehow, I mean, it's sounds fun, more fun to say one-dimensional than finite-dimensional, but of course, as long as the adjoint group has no anisotropic factor, smooth representation is irreducible smooth representation, finite-dimensional if and only if it's one-dimensional. So, I mean, that's usually the case you would be interested in. So, so that's just a remark. Yeah, I fix a parabolic, and yeah, for each parabolic, I have this. Yeah, and of course, I mean, P is a proper parabolic. So if G is somehow anisotropic mod center, then this is vacuous. And of course, if it's anisotropic mod center, then every representation is finite dimensional. Every E-reps are finite dimensional. So that's not an interesting case. And another remark, maybe I'm not going to write it down, but I assume that F to be a p-adic field, but I'm just writing down a conjecture, so no one stops me from, well, stating this for also local function fields. I don't know if it's true or not, but I think it's an interesting question. But the tools I'm going to use do not apply in the function field case. At least similar results may be true, but they're not available. So I stay on the p-adic case. Pardon? Oh, answers to Wittek's question. Sorry, maybe you. Oh, matrix coefficient. Well, that's in the proof section. Yeah. So yeah, just please bear with me, and I'll say something. Okay. Are there other questions, comments? So the thing is, well, I was not trying to ask this just out of nothing, but had some intended applications. So I wish somehow something like this was true, but I couldn't find kind of this thing in the literature somehow. I didn't quite find what I wanted. So, well, that's why I ended up trying to prove this. But these chances are, I mean, it may be known in some generality, but so far as I could find in the literature, these are what has been known. So if I have SP2N and unreified, then somehow motivated by some application to the Hecke orbit conjecture, well, Hecke equidistribution conjecture, I think Klosel and Ulmo proved the kind of rephrase of this thing, and in some way, that's, I think, in a paper published in 2004, and if I have a quasi-split classical group, then I've seen Tadic basically prove this. It's quite recent, actually, and it appears in the Shahidi volume, right? In a paper dedicated to Freiden. And of course, I mean, what happens in Tadic, I didn't have the time to read it too carefully, but I think he uses a lot of computation of induced representations and Jacob modules, maybe, and also reducibility and also classification of representations. So basically, the tools are somewhat specific to classical groups. They do not easily extend. Maybe you can get rid of quasi-split, but they may not easily extend. But that said, if you have some explicit classification results, this should be probably a matter of time. And indeed, if I have something like GLN over division algebra, then there's a complete classification of the unitary dual. I mean, in this case, the conjecture should follow from classification, which I believe is due to Tadich and Badolescu, Bernard, and Sescher. But you need to maybe compute a bunch of Jacquet modules, but I guess it shouldn't be too hard. So in that sense, I think the result is known in that case. Okay. So before I move on, are there questions? Yeah. Yeah. Mm-hmm. Mm-hmm. Right. Yeah, he must have had some weak version of this, right? Yeah. Maybe not exactly this, but some. Yeah, I mean, but if you can have any uniform exponent rather than 1/2, then I think it should work. But in that case, I guess you need also some uniformity over different primes. Yeah. Yeah. But actually, yeah, that's a great question. Actually, I don't know how he did it. So some result was known, you're saying? Available to Langlands. Okay. Yeah, maybe I would appreciate any expert comment. I mean, further comment on that. Yeah, that will be interesting to know. Our master Langlands probably knew something along this line. Okay, so now that I stated the conjecture, I'll state the theorem towards the conjecture. So theorem and proof. So my talk, maybe I should say something going back to the picture. Oh, yeah, maybe that would be instructive. So let me see. Maybe I'll apologize. Let me illustrate this example. So going back to this, back to GL2 or PGL2. So in the tempered case, what happens? And for concreteness, let's say nu P is P001, which is P positive if you take P to be the upper triangular Borel. In this case, for tempered principal series, what you're going to have is, well, first of all, this right-hand side of the conjecture is going to be square root of P. So that's the number to beat in part 1. And what are central characters of Jacquet modules in the case of PGL2 in the picture I described? If you have a tempered principal series, then left-hand side is going to be just 1. So Jacquet module remains unitary. So it's less than equal to 1/2, P to the 1/2. Complementary series, where A was between 0 and 1/2, you're going to get P to the A. So because A is between 0 and 1/2, still bounded by P to the 1/2, but strictly smaller. And in the case of trivial representation, LHA realizes the maximum, 1 P to the 1/2. And if I have Steinberg, then I'll get P to the negative 1/2. So Jacquet module breaks the symmetry, in fact, and then although they appear in the same induced representation, yeah, Steinbach doesn't achieve the equality. So that's I think a good example. Okay, so let's get to the theorem and proof. So let me first consider the simply connected cover of G. So that is the simply connected cover of the derived subgroup of G, and such a thing decomposes into finite product of restriction of scalars of some simple factors. So GI is also simply connected, and now the Dintin diagram will be connected. And theorem, we prove, is the following. Unfortunately, we have to assume something. And the condition may sound a little funny. Assume that for each I, if GI has rank 1, Fi rank 1, rational rank 1, then GI is quasi-split. It's really an artificial condition, but you'll see why I need this in the proof. Well, so this is one of those instances where higher rank groups are easier. And you'll see that. They're not always more difficult. Okay, I didn't state the conclusion. Then the conjecture is true for G. So that's the only condition. So in particular, you don't have to assume anything about G being classical groups or something. In particular, we deal with all the exceptional groups, because thanks to the fact that exceptional groups, even when you take inner forms, they tend to have kind of large rank greater than 1. Okay, so yeah, well, I'll just get to the proof. Oh, Fi is just some field, some finite field extension of F. Yeah. So when you have the simply connected cover, then you have such a decomposition into simple factors, and then I just want to say that if you have like rank 1 simple factor, then it has to be quasi-split, and you'll see why quite quickly in the proof. So the proof is the following. So it's relatively standard to reduce to the case where G itself is simply connected. Simply connected semi-simple group. The idea is basically you just pull back from G to G simply connected times suitable torus, say central torus. And there is a surjection of algebraic groups, may not be surjective on points, but still the co-kernel is finite, and somehow you can just pull back to this situation. And when you have this, then it's a product of kind of simple groups. So G has like also connected Dinkin diagram, if you like. So, so you can kind of sort things out according to the Dinkin diagram types, and well, you look at what kind of rank 1 groups you may have. But there is a kind of dichotomy here. So, of course, rank 0 case, that's, basically vacuous. And rank 1, well, if I didn't make a mistake, then for quasi-split rank 1 groups, they are either SL2 or SU3. And SL2, or could treat instead GL2 or U3 if you like. It's easy to go from GL2 to SL2 and U3 to SU3. So, there are some non-quasi-split. So these are quasi-split rank 1, and for non-quasi-split, there's some finite list, but there's somewhat a long list. I think things look like GL2 over division algebra or non-quasi-split U4, non-quasi-split inner forms of, or possibly outer forms, not here, but SP4, SP6, spin maybe 8 and spin 10, or something like this, maybe. I may have missed out a few, but well, so there are some things you don't want to look at. The way I deal with the rank 1 case is just go through classification results. So GL2, pretty much the picture I have shown you is a proof, because really, you just in general you consider some character twist of that, but it's really pretty much the same deal. And in the case of U3, things are more complicated, but don't know. Maybe I won't say much, but I just mentioned that I use results by Muich and Lapid, Muich, Tadic, and also there is a result by David Keyes and Rogowski. So, basically in the case of U3, I'll just say it and one write down. Basically, I divide into, well, you just consider principal series representations, and basically there are two cases. One is irreducible principal series, the other is reducible principal series. Irreducible principal series are generic by Muich, and then for generic principal series, Lapid, Muich, Tadic give you some sort of classification, and you can use that to check the conjecture. And in the reducible case, Keyes and Rogowski tell me what are the possible cases, and then you just check case by case. Okay, so now we move on to higher rank. That's most fun. Are there questions? Okay. So all of the main ingredients are, actually there are two ingredients. If I have to give a one-line comment on the proof, then there is a relatively not so well-known result by He-Oh bound on matrix coefficients. I think that basically partially answers Wittek's question on matrix coefficient plus Bernstein's stability. But in this argument, of course, an important point is nowhere we use classification results. In rank 1, somehow we had to resort to such results, so we missed some cases. In fact, GL2D case should follow. Actually, it does follow. GL2D is fine, but other cases, who knows what. But in higher rank case, we can use these two ingredients to completely answer the question. So let's see how this works. Let's see. So I need to introduce some notation for this. So I'll choose maybe T. For simplicity, the argument still works, but I'll assume G is split. Well, it helps me write things in a simpler way. So, and still simply connected and rank greater than or equal to 2. So we choose, and maybe assume that P is actually a standard parabolic. So we choose maximal torus, and B is rel. P is my parabolic subgroup. And then I also take K0 to be OF points of G, and I choose this over OF. And there's a open compact subgroup. Okay. And we have this Cartan decomposition. So G is decomposes over a set of dominant co-characters of K0 times mu of, well, that, I mean, var F is uniformizer of the p-adic field. So there is this decomposition, and correspondingly, I can write G equals K1 TG K2, where TG is just the mu of var pi f for some unique co-character mu, and has the property that actually it's for positive roots, the absolute value of alpha of TG will be positive, greater than or equal to 1. Okay. So let me recall what Heo's bound tells you. So let's say pi is unitary, but crucial assumption is it's infinite dimensional. And it's a kind of simpler version of her result. And then I take VW to be K invariant vectors in my unitary representation, which you can just assume to be non-zero by taking K to be small enough. And let's say these are unit vectors in the unitary representation. Then what do we know? Well, when you take the matrix coefficient pi g v comma w, then it is bounded by some constant depending on k times some funny product, well, alpha in some set of positive roots s of alpha of tg to the negative 1/2 plus epsilon So strictly speaking, I mean, this guy also depends on epsilon. But in fact, we can take epsilon to be anything, any positive number smaller than 1/2, so it doesn't really matter much. So that's the bound, and well, one of her motivations was to actually use this in some Hecke equidistribution result. Anyhow, well, that looks pretty good. If you can somehow relate Jacquet modules and matrix coefficients, So that brings us to the next result by Bernstein. So the idea is, well, you look at the double coset action on pi k, which is finite dimensional space, where it's enough to consider this for A equals nu p, where nu is a p positive cocharacter and, well, qualifies to be strictly dominant, whatever that means. But you just take nu p and it satisfies the condition. In this setup, and this is element in split center of M, you know the following. You take this double coset operator n times, which is a subspace of pi k, which you can map to the Jacquet module with k intersect M invariant. Then first of all, if n is large enough depending on k, then, well, this image stabilizes, and this map is an isomorphism. Moreover, you know the following. This double coset action corresponds to the A action here. Jacquet module is the M representation, so A acts on it. And, well, these are equivariant if you twist by delta p to the negative 1/2. So it's equivariant. K action is just A action. Okay. And using these two, you can pretty much close the deal. Okay, so let's really start the proof. So given exponent, so a central character in the Jacquet module, well, it means that there exists an element in here. Let's call it V0, on which A acts by this character. A acts by maybe omega times delta p1 negative 1/2. So omega appears on the right-hand side, and, well, just take k small enough so that Jacquet module has fixed vector under k intersect M, which you can do. And as soon as it's non-zero, you start to see this central character on the right-hand side of the isomorphism. So what do? Well, you look at V is some unit vector that corresponds to V0 under the isomorphism. And you compute this in two different ways. On the one hand, I mean, it's elementary to decompose this into, well, pi b VV, which is bounded by Hio. What is the bound? Well, some constant times, oh, I didn't say, sorry, what S was. S is some non-empty set of positive roots. Some set of positive roots. It may not be the set of all positive roots, but some positive roots. Okay, so CK times, well, this index of the double K in the double coset times this some, let's say it's to the negative 1/4 or something. Doesn't really matter. Any negative number is fine. So this part is going to be smaller than 1. So you have some power saving factor on the right-hand side. That's important for this argument. And if you choose K to be good in the technical sense, then KAK turns out to be just delta P -1 of A. Good. And what about another way? So this is O, and I apply Bernstein. Bernstein tells me that, well, KAK action is really just A action, which is a central action on the right-hand side, and central action is by this character. So it's just the omega times delta P A. Okay, so now you cancel out the coefficient, the exponents. I have -1/2. I have -1. Cancel them out. What you get is basically the conjecture, except up to a constant. Oh, where's the eraser? So the conclusion is this is, well, some constant times delta P -1/2 of A. Okay. And if you have been following, then that's what I prove. It's almost the conjecture, except that I have this unpleasant constant, but because this inequality holds for all powers of A, you can easily remove that, and that's the end of the proof. Thank you. Yeah.
So for temporal representation, what is the exponent delta P to the middle? Here is delta P to the -1/2.
Right.
For temporal representation, what is this?
The right-hand side is always given by some number. As if, for instance, in the case of GL2, I gave you something like P, square root of P, but then here, for temporal representations, sometimes it's 1. For something like Steinberg, it could be P to the -1/2. So it depends. Yeah. You don't have a uniform answer, but yeah, you have, but for temporal representation, the left-hand side tends to be smaller, and when you have non-temporal representation, the left-hand side tends to be bigger.
Yes, presumably for some groups, this -1/2 is not that.
Still, it's achieved by one-dimensional representation. So the bound is good. I mean, the equality is achieved by one-dimensional representations. But the question, I guess, going back to Ali's question, is what is the next most temporal representation, non-temporal representations? And then I think the answer can be very interesting. And actually, O has something to say about that, namely, I mean, the whole philosophy here is that when you have rank greater than or equal to 2, then this group has Kac-Dan property T, which means that the one-dimensional representations are isolated in the unitary dual, and now you want to kind of bound how far one-dimensional representations are from the rest. And there's some numerical bound on this. So I think one can prove some result in this direction. So in other words, for the next non-tempered guy, maybe you can save the power, hopefully, but I don't think that's quite right. I think what seems to happen is you can save the power in some direction of root subgroups, but not in all directions. Right, yeah. Oh, did I forget to say that? Oh, yeah, I did. Yeah, right. For infinite dimensional representations, right. For that, actually, because this is strictly less than 1, I have, in fact, strict inequality. Yeah. Because you can kind of make this, if this is constant and this can be arbitrarily small if you raise A to some power. So, in fact, you always have strict inequality. And then for finite dimensional representation, you just go back and see that actually the equality holds. I think O's bound says that the matrix coefficients are bounded for all infinite dimensional representations, so I think the only candidates are finite dimensional ones, or typically one-dimensional representations. Pardon? Right. Conclusion. I don't see a direct implication between the two, so maybe you can tell me afterward. I mean, I used bound-on matrix coefficients as an ingredient of proof, but I don't see like direct implication between the conjecture and the bound-on matrix coefficients without going through some computations. So, and this is, I mean, at the moment the best I've got, but maybe there's a better way to think of it. So yeah, I'm happy to hear your further comments.